Lecture 6, Significant Figures and Scientific Notation. How many significant figures are present in each measurement below? Well, by the rules from your textbook, when we have any non-zero digit is significant. So 6, 5, and 3, none of them are zeros, so there must be 3 significant figures. Another rule is that if you have a non-zero digit on each side of a set of zeros, these are called confined zeros, the zeros then are significant. So there's 5 significant figures here. And the reasoning is that if this digit is significant and this one is, so where the ones place and the tens, hundreds, ten thousands place are both significant, then the ones in between have to be. The zeros there just happen to be what the measurement is. Another rule is that leading zeros are not significant. They're placeholders. So there's only 3 significant figures here. So anytime you see leading zeros, these are not significant. Now if we go back to the one above, we're free to do that. Notice we can add as many zeros as we want to the front. It would look a little bit weird. People would be looking for a decimal place, but if they saw none, they'd say, well, this person just likes zeros. There's still just these ones here. So the leading zeros are never significant. This one gives us a little trouble. Trailing zeros, if there's no decimal place, may or may not be significant. So we can't say. We can say at least 3 significant figures, but we can't say anything more. Now if we did this and we put a decimal place there, then 5, definitely. But because these zeros may just be placeholders, they may simply be putting the 2 in the hundreds place where it needs to be. So the only way to know for sure is to go to scientific notation, because scientific notation, the numbers that are present are always significant. That's the purpose of the scientific notation, or one of the purposes. So here we are. Convert these numbers to scientific notation. Now the rule is you only have one digit to the left of the decimal place, so we write it like this, and then we multiply it by 10 raised to some power, and you can do it either just by the rule of you just move the decimal place over to the left twice, so this is a 2. But if you want to fully understand it, think of what this is. 10 to the 2 is 100. So 1.67 times 10 to the 100, or 10 to 100 is 167. So we're back to the original number. So that's all we're doing. So is just taking a number that's always between 0 and 10, greater than 0, less than 10, and multiplying it by some power of 10. If we look at this number, we move the decimal place to the right, 1, 2, 3, so it'd be 10 to the minus 3, and 7.156. We can't lose any of those numbers, we have to keep them all. 10 to the minus 3 is 1 over 1,000 times 7.156, and that would give us back our original number. So you can just learn it as that's what, moving this decimal place over gives us this number, but you should understand really at this point what's going on as far as the math. It's the same number, it's just in a different form. Notice here we have 56,000 and there's no decimal place, and we have these trailing zeros. You have to specify how many sig figs we have. So this 0 is the last measurement that we did, last digit that we measured. It just happened to be a 0. Could have been a 1 or 2, and that would have made our life easy, but it was a 0. So we put 5.60. We don't put in the others. Those others are just placeholders, according to this statement here. So times 10 to the 1, 2, 3, 4. The decimal place isn't shown because it's not that these zeros aren't significant, but it's there as far as if we want to count over and make a significant or a scientific notation. 56,777. Now this would be kind of a waste to do this because all we're doing is making work for ourselves. we have to put in all the digits because they're all non-zero, so they're all significant, they all go in. But always 1 to the left, all the way up. This guy, all these leading zeros, none of them are significant. So, and when you say they're not significant, you don't say they're insignificant. So they're significant figures, and then there are numbers that are not significant figures, rather than insignificant. So this one, all this is a little tricky. It's 6 times 10 to the 3, 6, 9, 12, 15, 18, 21. Minus 21. So you can see here, this one, it's not worth it to change over, unless somebody tells you to do it as part of a problem, but you wouldn't do it normally. But this one definitely would be worthwhile because you wouldn't want to have to write all those zeros all the time. And then let's convert back. So we have 5.11, and we'd go 1, 2, 3, 4. So it'd be 51,100. And what we'd have to specify is that there are 3 significant figures. Then we have 8.89 times 10 to the minus 3, so 1, 2, 3, like so. And then I'm just going to use it from here since we have 10 to the 5th, so it's going to be 1, 2, 3, 4, 5. Oh, okay. So 6, 8, 9, 7, 8, 9. Is that right? Yep, okay. And then 5 times 10 to the minus 15. This one is just to be annoying, so it'd be 5, actually. Put the 5 over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Kind of messy, but that's what you would have. And there you go.